Hi there. This video is on the topic of interference of light and its applications in communication systems. So this is the formal definition of interference of light. When multiple coherent light rays arrive at a point, the resultant ray of light is the vector sum of all individual light rays. But the one that I like more is that of mixing of light or fluids or colors or paint or anything for that matter. So this video shows the mixing of light, or in more formal terms the interference, and as you can see the interference of red, green and blue, the RGB gives of white light right in the center spot. So I would just let the video play here, as I don't think that there is any need of further elaboration. So when I first heard about this phenomenon, I tried to do what other children of my age also tried to do, and that was mixing all those three colors, that is red, green and blue. But to all our doom, the result was black and not white. This is the point where most of us started becoming skeptical of the parents and elders. But putting that tangent aside, let's try to understand what actually happened. Paint is a little different from direct light, in that it actually absorbs most types of radiations and reflects only certain light, which is what we call the color of the paint. So yellow absorbs most of blue and green and some of red of high wavelength, and reflects back the rest, that is yellow mostly. And so we can imagine what will happen if we mix all the colors. Each color will absorb most of light in different spectrums, and we will get black. Now let's get to the topic at hand, which is applications of interference in communication systems, which is literally everywhere in signal processing. Whenever we are talking about signals, odds are it has experienced some amount of interference engineered by humans. This section is so vast that there are whole programs named after it. We will explain something more simple and digestible for our audience and for our own convenience. We will explain modulation. Modulation can be considered as the manipulation of signal for better performance. But first, what is the need for modulation? Why bother with it at all? If you have studied some high school science, you must know that the speed of light is constant and is in fact the product of its frequency and wavelength. This implies that for lower frequencies, the wavelength will be higher and vice versa. They are inversely proportional, if you prefer that term. So the audible frequency of the human ear is 20 to 20 kHz roughly, and we think about sending a signal with this frequency at the speed of light. The wavelength must be around 15 kilometers at least, and hence height would actually be proportional to that. So now we know that we need to change the signal for practical transmission. This change is what electrical engineers call modulation. The solution is to superimpose or interfere a carrier wave of sufficiently high frequency over our original signal. But there are also some constraints to it that have been developed so communication standards are maintained, and hence there are mainly two types of analog modulations. First, amplitude modulation. Here the original signal is used as reference to manipulate the amplitude of the carrier. So as you can see, the amplitude of the modulated signal is following that of the modulating signal. Second, frequency modulation. Here the amplitude of the original signal is used as reference to manipulate the frequency of the carrier. Now bear with me for a sec. The modulated signal is actually a little shifted towards left, but you can still understand the concept. That is, the amplitude of the modulating signal dictates the amplitude of the carrier. I would like to thank Box Physics and Elesics for their videos on interference and modulation respectively. And I would also like to thank our team for making this video, and without them it would have been impossible actually.